The population of Australia in 2000 was 19.2 million people. In 2010, the population grew to 20.9 million people, assuming it follows the law of uninhibited growth. So that law goes y equals c times e raised to the kt power. C stands for the initial amount or the initial quantity. Y stands for the new amount after t time has gone by. Letter K is what we call the exponential growth constant. And the first step is going to be to always solve for letter K, and we're always going to round to 4 decimal places. So here, the population of Australia in 2000 was 19.2 million people. So I'm going to make the year 2000 the initial starting point, which means the initial value, the initial amount, was 19.2. I'll keep everything in terms of millions. The new amount is going to be in year 2010. The population grew to 20.9 million people. So the new amount, the new value is 20.9, and the time, well, since we started in the year 2000, now we're up to the year 2010, the time is going to be t is equal to 10. So my first step is going to be to plug in my y, my t, and my c into this law of uninhibited growth and solve for letter k to 4 decimal places. So I'm going to be left with my y value, so that leaves me with 20.9. So that equals c, which is 19.2, times e raised to the k times t. Well, in this case, t is 10, so 10k power. So my first step is going to be to solve this equation for letter k, and I'm going to solve for k graphically. I'm going to set the left-hand side of the equation to y1, the right-hand side of the equation into y2, and find the point of intersection. Now, letter K stands for the exponential growth constant, and letter K is always going to be a decimal in between -1 and +1. If your change is decreasing as time goes by, you're going to have a negative k value. If your value is changing and it's increasing, you're going to have a positive value. So here's what my calculator looks like. I have my left-hand side in y1, the right-hand side of the equation into y2. I have my x-min and my x-max to be -2 to +2, so that gives me a little bit of room because k is always a decimal between -1 and +1. And here, since I have y1 is 20.9, I made my y-max 25 to make sure that fit on my graph. So I'm trying to find the point of intersection of the left and right-hand side of the equation. And here is my point of intersection, and here's what matters, letter K. Letter K to 4 decimal places is going to be 0.0085. And that makes sense because the number of people in Australia is increasing, so K is a positive value. So now what I'm going to do is I'm going to take all of those values. I have my y equals c times e to the kt power. For this problem, k is going to be equal to 0.0085. What's also not going to change here is my initial value. I chose to let 2000 be the starting point, so here my initial value is going to be 19.2. So for this question, the equation that models Australia's population, y equals c, which is 19.2, times e raised to the k times t, so in this case 0.0085 t power. And what I'm going to do is I'm going to enter that now into y1 in my calculator. So I cleared out my old y1 and y2 and I typed this equation into y1, and now I'm going to use my calculator to go about answering these questions. So in problem B, calculate the population of Australia in the year 2015. Since I chose the year 2000 to be my starting point of my problem, I'm just going to go to my table. Since I have the exponential growth constant in the equation for this problem, I'm going to go to my table and just look at the value when x is equal to 15. So here the population of Australia in the year 2015, according to this exponential growth model, is going to be, and I'll stick with the same unit of measure, 21.8 million people. 21.8 million. If I needed to get a more precise answer, I just simply highlight and I go down to the bottom here. So here it would be 21,810,909 people. But this particular question was going to the nearest tenth of a million, so I kind of stuck with that notation. For part C, in which year will the population of Austria, which is going to be tough to answer since I'm dealing with Australia, in what year will the population of Australia first surpass 30 million people? So what I did was, I entered the equation y equals 30 million, so y equals 30, into y2, and now I'm going to go about finding the point of intersection of those two values. The only difference is I'm going to have to change the viewing window from what I had said previously, because before I was solving for letter k, the exponential growth constant. So here is the viewing window which I'm choosing to use for this question. I'm looking for my x value. When will the population reach 30 million? So I'm going to look from the year 2000, which is x is equal to 0, to the year 2100. So that's why I set my x-min and my x-max to 0 and 100. And as far as the y's go, here since I am graphing y2 is equal to 30, I chose to set my y-max be equal to 40. And now I'm going to look for the point of intersection of these two lines. So I got my point of intersection to be right up here, 52.5 comma y is equal to 30. So in which year? Well, since I chose 2000 as the starting point, this looks like it would be the year 2052.5, so somewhere in the 2052-2053 range. That's when the population of Australia should reach 30 million for the first time. Problem 2, the number of bacteria in a certain culture follows the exponential growth model, so y equals c times e to the kt power. Initially, there were 100 bacteria, so that's going to be my starting value. C is going to be 100, and then after 5 hours, so after t hours, t is 5, there are 300 bacteria. So y, the new value, is going to be 300. So the first step, even if it doesn't say so, is to figure out what our k value is. And remember, we're always going to go to 4 decimal places. So I'm going to plug back into this exponential growth model. Here I have my y value, so that's going to be my 300. That equals letter C, the starting amount. So that's going to be 100. Times e raised to the k times t. In this case, t is 5, so 5k power. So I'm going to go about finding letter k. I'm going to solve this equation graphically by entering y1 as 300 and y2 as 100e to the 5k. I'm going to find the point of intersection. And here, the sign of letter k. Here the bacteria is going from 100 up to 300. So since the growth is in a positive direction, when I go about finding my k value, I know that k should be a positive value. So I entered y1 as 300, y2 as 100e to the 5k. And remember, k is always a decimal in between -1 and +1. So I'm setting my x min to be -2 and my x max to be +2 because x is letter k, that's what I'm solving for. And here, since I'm graphing y1 is equal to 300, I'm choosing to make my y min 0 and my y max 400. So here, when I find the point of intersection of the two sides of the equation, here I'm getting k is going to be a positive value, which is what I suspected, and k is going to be equal to 0.2197. We're always going to be rounding our k value to 4 decimal places. So here, for this particular problem, the model that we're going to be using, the equation that we're going to be using to answer this question, y equals c, the initial amount is never going to change, that's going to be my 100, times e raised to the k times t, well k was 0.2197 times t power. So this is going to be the equation that I'm now going to be using to answer the questions in this part. And once you find your letter k, I suggest you clear out your two equations and enter this into y1, and then use your calculator to answer the parts of the question. So problem B, calculate the number of bacteria that will be in the culture in 10 hours. All I'm going to do is plug in 10 for letter T, which basically means I'm going to go to my table and look at my value when x is going to be 10. So here it looks like after 10 hours there's going to be, I guess I'll round to the nearest bacteria if that makes any sense, there's going to be 900 bacteria present after 10 hours. Letter C says after how many hours will there be 1,000 bacteria? Well, it looks like it's going to be in between 10 and 11 hours according to my table. After 10 hours it's 900, after 11 hours it's 1120. What I'm going to do though, if I needed to go to the nearest tenth of an hour, I can just enter in 1,000 now into y2 of my calculator and find the point of intersection of those two equations. Remember though, I need to change the viewing window. I only have my x's going from -2 to +2 because I used it to find my k value. And according to my table, I know my answer is in between 10 and 11 hours, so I'm going from 0 to 20 hours for my x's. And then my y's, well, since I'm graphing y is equal to 1,000, I chose to make my y max 2,000, so that way I'd be able to see that line. So the point of intersection of these two equations is going to be the number of hours it takes for the bacteria to increase to 1,000. And it looks like here it's going to take about 10.48, so maybe if the directions say go to the nearest tenth of an hour, it's going to take about 10.5 hours for the bacteria to increase.